All right, good afternoon, my EM aficionados. So as promised in the beam shift trackball quick hitter video I did yesterday, I'm going to go over today a little tutorial here about how to do 4D STEM using TIA and or TIA and your Ceta camera, okay? So I did tutorials before showing how to do, collect 4D STEM data with the EMPAD, okay? So we should probably start by talking about, well, why on earth would you want to do a 4D STEM experiment using TIA and your Ceta camera, okay? If you have an EMPAD, so the only real advantage of the Ceta camera over the EMPAD is pixel resolution, okay? So your EMPAD is 128 by 128, but your Ceta camera is 4K by 4K. Now we can't read the entire 4K by 4K area from the Ceta camera because of the HADF detector. So if I actually show you this, right, this is the HADF detector schematically indicated here, approximately, and that is the pixel at the full sensor area of the Ceta camera. So basically the only area that we can really read is right here in the middle. So this is, I believe, if we look here, let me find it. Yes, so this is basically, if we were trying, this is, yes, so basically we can read out 1/8 the width of the full width of the pixel array without any obfuscation or blockage by the HADF detector. If we bump this up to 1/4, then part of this is going to get cut off, okay, around the outside. So we could technically do 1/4 if we wanted to, but you're going to end up with some loss of information out here. But if we do 1/8, we don't have any loss of information here, okay? So, and so we could, if we're just reading out 1/8 here, okay, because again, we have 4K by 4K resolution, we could acquire this 1/8 of, or 1/8 of the width, I don't like that it says 1/8 of the readout area, right? Because really it's not 1/8. It would actually be a 64th if you think about it, but because it's an area, right? But they call it 1/8. Anyways, we could read the 1/8 of a readout area with actually up to 512 by 512 pixel resolution, or as low as 256 by 256. Either of those is a big upgrade over what you get with the EMPAD, right? Because you're talking about 4 times as many pixels if you go up to 256 by 256, and then if you go to 512 by 512, then you're talking about 16 times more pixels, okay? So that really is the main benefit of using the Ceta camera, okay? Apart from that, there really isn't a benefit to using the Ceta camera, okay? So the EMPAD has higher dynamic range, and you can acquire, as we're going to see here, you can acquire the data about 100 times faster with the EMPAD than you can if you use TIA and the Ceta camera, okay? You can acquire EDS at the same time when you collect a 4D STEM data set with TIA, but your beam currents when you're doing 4D STEM, because again, you have to remember, right, you don't want to fry your camera, they're very low, okay? So we're only going to be around like 10, 12 picoamps here. So trying to do EDS with 10 to 12 picoamps, even if you have a really good EDS detector, you're basically not going to get anything useful, okay? So even though you could technically get EDS at the same time, if you're using TIA, the EDS data you're going to get is going to be basically just, it's going to be almost, what's the word? I don't want to say noise, but, not useful, right? But just not useful, right? In any capacity here. So now, of course, if you don't have an EMPAD, right, then you would have to use the Ceta camera. There is an option to do 4D-STEM inside of Velox, okay? Unfortunately, that is an expensive option. You have to pay for the upgrade. That is not just a stock option in Velox. There is a software update that is required for that. Additionally, depending on the type of SATA camera you have, on this system we have what's called the speed upgrade, okay? So what that means is, if I go here to Velox here, and I pull up, where is it here? Detectors, SATA, and I reduce my readout area to 1/8 here, and I put in 0 here for the exposure time, okay? So I can read out the smallest area at 3.12 milliseconds per frame, okay? If you don't have the speed enhancement, I believe that this number is 4 times as high, okay? So if you have the ability to do 4D-STEM inside of Velox, you can collect the data this quickly, okay? You can collect the data at 3 milliseconds approximately per diffraction pattern. If we're forced to do this using TIA, the synchronization between TIA and the SATA camera is not as precise, okay? So we're really limited to how fast we can go with TIA, okay? And it turns out we can't really go faster than about 100 milliseconds a pixel if we do the 4D-STEM experiment with TIA, okay? So think about that. That's 100 times slower than what you can do with the EMPAD, okay? And it would be, what would that be? That would be about 33 times slower as what you could do with Velox if you have that option as well, okay? We can use drift correction when we're doing TIA. We can't do that if we're using the EMPAD, okay? And so if we're actually taking that long to collect the 4D-STEM experiment, it actually becomes rather important to be able to drift correct. So that's something we will talk about. And you can't drift correct if you're using the EMPAD, right? There's no option for that. But again, since you're going at a millisecond a pattern, your data is acquired so quickly that your susceptibility to drift is much less than it would be if you're going at 100 milliseconds a pixel, okay? So anyways, kind of just, a little bit of a backstory here, but I thought it was important to mention this. As far as how I have the microscope set up here, so I'm in STEM mode already. I am in microprobe mode with the smallest C2 aperture and my value of alpha dialed down to the smallest possible number, and I'm at spot size 10. So if I unblank the beam here, let's see here. Okay, this is about 12, 13 picoamps, okay? So again, I've got the monochromator on this, and I've got the monochromator at minus 40, okay? So again, under these conditions, I'm getting about 12, 13 picoamps. If you have the speed enhancement to the SATA camera, this should be safe for collecting your 4D STEM experiments using a camera length as low as 91 millimeters, okay? Because you want to avoid saturation, right? You don't want to end up burning your SATA camera. But even at only 12, 13 picoamps, we have to be careful in terms of potentially damaging the scintillator, okay? Because we're putting that current into a small number of pixels. Now, of course, this is just the beam in vacuum right now. Okay, we're in vacuum here. When we're going over the actual sample, it's going to get distributed over, other spots, so it's not going to be all consolidated within that, but you want to verify for safety that when you're in vacuum, that you're not going to have a problem. So I actually know, because I've already tested this, that again, at 91 millimeters and with these beam conditions, that we shouldn't have a problem. Again, with the speed enhancement to the SATA camera, which allows us to take an individual frame over 1/8 area as quickly as 3.12 milliseconds, okay? So, kind of wordy there, but, just what I wanted to go over. So with that, I have a tab here specifically for TIA experiments. There was another panel down here for the camera, which is not here anymore because of the way the screen capture works, so we can pull it up over here, okay? But we're going to have to make use of this at the same time, okay? So with this, I'm not actively inquiring inside of Velox. I'm going to pull up TIA, and I'm going to start searching here. So we're going to get a STEM image here. You can optimize your detector contrast and brightness inside of Velox, and then it should be fine inside of TIA. Otherwise, if you want to do this inside of TIA, we can turn on the scope. And since we have the layers running horizontally here, if we do a relative rotate by 90, this kind of allows us to see this better. So if I click on multifunction knobs inside STEM detector, you can see here I'm starting to get clipping. So, and again, that's, and there's the clipping there. Basically, somewhere in there is good. Again, this doesn't impact the actual diffraction patterns, but you want this, dialed in well here, just for when we, when we collect the image to help with like drift correction and whatnot. So we're going to leave this at that. Let's turn off the scope, and then I'm going to rotate this back to 90 degrees, and then I am also going to. So this is the surface. So let's talk about the sample here. This is the surface of the sample. There's an oxide on here. There was a thin layer of nickel on a silicon wafer, which was then laser annealed. So that's what this layer is right here. This is a nickel silicide, and then you have silicon. This is E-beam platinum from the lamella prep, okay? So you can see that this is not quite flat. So if we go to the slider here, if we click on this, and then we use our arrows left and right, we can change our rotation angle in 1/10 of a degree increments. If you go over here to the square annotation, you can draw this to make sure that it's nice and even. You did notice I bumped up the dwell time here because otherwise that can kind of interfere with how this looks. But yes, you can see this is nice and flat. One thing you can do too inside TIA, there isn't a default for this in TIA, but if you come over here and you find your beam position marker tool, if you click on this and then you click right here, when you stop the scan, the beam will go right here. Okay, so it's not pasting over your sample. But the area that we're interested in doing the 4D-STEM on is the silicide, okay, and maybe a little bit of the silicon. And we could probably get just, a little bit of the underside of the platinum strap as well, just, to include that. If you add a rotation here to the STEM image, your diffraction patterns will not be perfectly aligned, right? So the STEM image, if you rotate it, in this case, that was a counterclockwise rotation, I believe. Let me check this here just to be sure. Yes, that was a counterclockwise rotation. So what you would have to do in order to get the diffraction patterns to perfectly align with the image, you would have to rotate all of your diffraction patterns by 1.2 degrees counterclockwise as well, okay? In order to make sure you have the proper rotation calibration between the image and the diffraction patterns. If you don't adjust the scan rotation, then you don't have to worry about that. But obviously, you want to adjust this if you have like a film like this because it's more efficient as far as collecting the data, okay? So this is okay here. What I'm going to do now, let me drop this down here, something short, and I'm going to actually put an image position marker, which is this guy, and click on it. And so now this is a 512 by 512 image. If I double left click, and you can see here the position is indicated in pixels. So if I put 256 by 256, that's basically dead center now in the image, okay? So I'm going to move this off of here, or actually, well, I'm going to actually delete this and do this with the beam position marker. Okay, and then I'm going to stop, And now I'm going to go to my CCD /TV camera panel. Now, of course, this is actually a CMOS camera. It's not actually a CCD, but it's kind of neither here nor there. Okay. So now we need to talk about how to set up the parameters here for your CETA camera for when you're going to acquire the 4D-STEM data. Okay. So the way this works is whichever one of these settings you have activated, it could be search, it could be preview, it could be acquire, it doesn't matter. Whichever one of those you have last activated, that's what TIA is going to use when it acquires the data set, okay? So for, the easiest thing to do is you could have these set all to the same thing just to make sure that you don't, mess something up. Or if you want to do this with just acquire, you could just set it to acquire, okay? So if I set this to acquire, okay, and I don't have a beam because my screen is out of the way, which is fine. But before we do that, let me go over a couple things here. So again, right, we're using 1/8 of the readout area, okay? So that, again, that ensures that we're not getting any blockage by the HADF detector, okay? Sorry, let me go back. Okay, so we're using 1/8 of the readout area. We're going to use binning of 2 to keep the size of the patterns manageable, right? Because if we include more pixels, the size of the pattern is going to be larger and it's going to take up more memory, okay? But you could do this with 256 by 256. If you increase the binning further, it has no impact on this. So actually you can see right here, if I right-click info, you can see it says 256 by 256 with binning 2. If I increase this to binning 8, and then I go to info, it didn't change the pixel dimensions at all, okay? So keep that in mind here. Even, unfortunately, there isn't any way in the software to, it says it's 64 by 64, but it's really not, okay? So you have to just be aware of this. As far as the integration time, so this is critical that you have this set properly, or else you're going to end up with patterns that are smeared, potentially, or the data taking longer to collect than usual, okay? So again, because we have the speed enhancement on this system, we can collect images with the CETA camera over 1/8 readout area as quickly as 3.12 milliseconds per image, okay? So you can see right now I have 50 milliseconds as my integration time, okay? So if I take 50, and I divide by 3.12, okay, I get approximately 16, okay? So basically I can sum 16 frames over 50 milliseconds, each frame being approximately 3.12 milliseconds, okay? So this is a safe way to use a longer integration time by spreading it out over more frames, okay? So you might be saying, well, why don't we just reduce this to like 3 milliseconds in one frame? The problem if we do that is we're gonna end up with patterns that end up looking smeared, okay? This is the issue with the synchronization between TIA and the camera. So we need to use a longer integration time. So what I found here is using 50 milliseconds and doing frame combining of 16 frames works perfectly for this, okay? So then the rest of the settings in here, you want rolling shutter off, you want noise reduction off, obviously you want bias and gain corrected. If you go to mode, you want mode on continuous, okay? And the rest of this is fine, okay? So I'm gonna leave this on, and now inside of this is where the diffraction pattern is gonna be. I'm gonna click on image position marker, double left click, and then I can uncheck display in pixels, and now this is in reciprocal nanometers, so if I put 0, 0, that's going to put me dead center. And so now, when I move the screen out of the way, I can use my diffraction shift to center my direct spot right here, okay? So I'm going to go to direct alignments, diffraction alignment, And now I'm going to pull my screen out of the way, and there we go. Okay, and I'll go to put the screen back in. Okay, and now we have our CETA camera set up exactly how we want it. Okay, so I'm going to go ahead and push acquire to stop the acquisition, and then we can come back to the actual STEM image here. Unfortunately, you can't run these at the same time like you can with Velox. So we're going to go ahead and click search. Okay. And now we can, so this is in the center here, remember? So I'm going to move this out of the way. This is going to be our park position, and I'm going to go back to an image position marker, double left click, and then I'm going to put this at 256 by 256, so that's in the center. Okay, so now we know what's in the center. So we want to keep our area of interest in the center of the image as much as possible, because that's going to keep any shifting of the pattern as it scans over the image area as minimal as possible. That's the descan artifact. Okay, we can bump this up here, and then we can just optimize our focus here a little, so I can actually turn on the focus box. Okay, we probably have a little astigmatism here, so let me see. You know, it doesn't look too bad. Maybe there's a little bit there. I'm turning on the condenser stigmators here. Okay, that looks okay. All right, let me mag back out here. Okay, and then I'm going to stop this so my beam is out here so it's not over the sample. All right, so let's talk about how we want to sample this. So we can calculate the size of the beam based on our known parameters, okay? So again, we've got 13 picoamps. Our semi-angle of convergence, if we pull up the beam settings panel, it's indicated as 0.48 millirad. In reality, as I think I've mentioned in several other videos, in microprobe mode, this is actually about twice as big as this, okay? So really it's about 1 millirad. So based on that information, we can pull up S-core, and we can calculate a probe size. So if you go to where it says C1A1, click options, enter in your probe semi-aperture angle in millirad of 1 millirad, and then you come over here where it says probe current, so it says 12 here. It's not really going to be that much different if we put 13, but we'll go ahead and put that in. Okay, and then click update. And so it's saying that our probe size is approximately 1.6 nanometers, okay? And that makes a lot of sense considering that our semi-angle of convergence is really small right now, okay? Right, so if we go down 1 picoamp, it's actually getting us to, 1.4 nanometers. So, all right, we'll leave it at 13 just for consistency's sake. Okay, so what does this mean? So, when we're collecting the data, we don't want to exceed a pixel size that is half of this number, okay? If we exceed a pixel size that's half of this number, then we are no longer getting any benefit, okay? So you might ask yourself, well, why don't we just make the pixel size equal to this number? So that would be perfect sampling. In reality, we can exceed that number and we can oversample to the point where we're using a pixel size that's about half of the probe size, because again, if you remember the Nyquist-Shannon sampling theorem from the FFT video, right? So the information limit is about twice the pixel size, okay? And of course, we can never resolve anything smaller than the size of the probe. So, therefore, twice the pixel size equals the probe size, okay? So therefore, our minimum pixel size would be approximately half of the probe size, okay? At which point, we're not going to see any additional information, and we're just going to be kind of oversampling needlessly, okay? If you oversample excessively, you're looking at issues with like damage to the sample, potentially. So that's why it's important to not, oversample unless you have to for some reason. Again, like for what we're doing here, there's really no point. So basically, I would make the probe size between 1.6 and 0.8 nanometers, okay, somewhere in there, to ensure that we're optimally sampling our sample here, okay. All right. So now that we know that, we can come back here, and now what we can do is we can acquire an actual image. So we're going to go ahead and click Acquire here. I have this set for 1K by 1K and just 10 microseconds. And now I'm going to come over here and click Beam Position Marker and click up here in the vacuum so it's not going onto the sample. And so now, there's a couple ways to do this. So if we right-click on here and go to Info, we can see the pixel size right now. So the pixel size is a little bit less than 400 picometers. Okay, so if we know that information, we can set this up accordingly. Otherwise, we can actually directly manipulate the size of the pixel in the 4D-STEM map as well, okay? So I'll show you how we can do that. So for the sake of simplicity, if we target just a pixel size of 1 nanometer when we're doing the map, that's going to make things pretty easy. So now what we can do here is go to Experiments, and we want to do spectrum collection, and we want to do a drift-corrected spectrum image. So we definitely want to drift correct here because this is going to take considerable time to do, and then we can click Add Markers. And so we see 2 markers here. So the orange is where the data is going to be acquired from, and the yellow is what's going to be used for the drift correction. Okay, so you can change these, obviously. So if you double left click on the yellow, what I'd like to do here is actually reduce the size of this. So this is defaulted to 256 by 256. I will cut this down in half. Whoops, if I can type properly. Okay. And then I'll put this. So now ideally, you want to put this somewhere where you've got like some structure, some like two-dimensionality. So something like this should work pretty well. Because we have these like this wavy line here in the E-beam Platinum. So we'll go ahead and use this. And then this is going to be, so if I double left click on this, it says enter position using center and size. So if I put the center as 0 and 0 and click apply, oh, whoops, no, let's uncheck this. Okay, so we'll do it in terms of center. Let's see, if we do 0 and 0 and then apply. Okay, that brings it back to the center. Okay, so I uncheck display in pixel. So now we can make this as wide as we want. Okay, so if we make this, say, 100 nanometers wide by 50 nanometers tall, okay, and then if we make the number of pixels 100 by 50, then the size of our pixel would be about 1 nanometer. Okay. We could also change the number. So in other words, so if we wanted to say instead, if we wanted to use 0.8 nanometers, so we could just do 100 divided by 0.8, and then we would have to tell the system to do 125 pixels here. But we'll go ahead and just leave this. Well, let me make this a little bit. We'll go 150 by 75. Since we want to get a little bit of everything in here. I'm going to go a little more. We'll go 200. Okay, just like that. Okay, and so now we're going to come over to the experiments panel, hit the flap out, And so now here's where we tell it the number of pixels, okay? So again, right, since we made this 200 wide, 200 nanometers wide. So if we change this, the X dimension to 200 nanometers, that's going to give us a 1 nanometer pixel size. If you keep fixed direction X, then the Y dimension will be calculated automatically, so you don't have to enter this manually, okay? So it should end up being 75 nanometers because we specified the dimensions of the box to be 200 nanometers by 75 nanometers. As far as the dwell time, we have to set this now to be 50 milliseconds, okay? Just like what we had here for the CCD TV camera setting, again, for acquire, okay? So let's not worry about EDS here. We do want to acquire a CCD image. Yes, we're acquiring STEM. We want a blank when we're done so we don't paste the sample. And then, yes, we want fast acquisition mode on. And we can minimize this. So now, for the drift correction here, number of acquisitions in slice. So basically, the way this is set up, it's going to do 200 pixels, which is one row, and then do a correction. Okay? We manually change the size of the image to 128 by 128, so we don't have to worry about that. If we didn't, it would be at 256. It's going to use 8 microseconds as a dwell time when it's doing the reference image. Number of slices per reference. So basically, a slice is each drift correction. So basically, each row is a drift correction. So the number of rows is 75. So that means there's going to be 75 slices in total. So this number is much larger than that. That ensures that a new reference image is never collected, okay? Which is usually the best approach. And then predict drift rate, yes. And then the default for this is usually to have use MCF set to yes, and the rest of these are grayed out. MCF is mutual correlation function, and so that's what it's usually defaulted on. That, I believe, when I checked the manual, it says that is useful for suppressing the effects of like strongly periodic features in an image. But again, this is the default. If the drift correction doesn't work well for this for some reason, we can change this to other settings and see if it maybe works a little bit better, okay? But as far as I am concerned here, everything looks good. All right, so now, we've been a little while here, so I'm going to click refresh here, and that's just going to take another STEM image. Okay, get everything in position here. And we are good to go. And then we're going to hit acquire. And hopefully this works. Oh boy. Okay. I forgot to pull the screen out. All right, let me pull the screen out. Okay. All right. All right, so what can we do here? Let's just unblank the beam. Hit refresh, click OK. It's going to take a new image here. All right, let me take another one here. Sometimes there's a little bit of Let me do another one here. Yeah, don't forget to pull the screen out of the way. All right, I think that's good. And then we can just click reacquire and it'll just use the same panel. There we go. All right, so if we click on this, we can digitally adjust this here, and there we go. So we can see the patterns here. So now, again, with TIA and the Ceta camera, you cannot acquire data faster than 100 milliseconds a pixel, okay? So let's do a little timer here, and let's see. So it should be taking 20 seconds to get across a row, okay? So I'm gonna just time this here. The next time it starts a row, and we'll we'll see how well it's doing that. Okay, yeah, so it's working. So it's taking about 20 seconds a line. So yep, it's doing its minimum time. You can see here with the patterns that we're not exceeding 8,000 counts, right? You can see the max line. Well, when I go away, when I move the mouse, it goes away. But yeah, we're not exceeding, we're not saturating the camera. So everything's good in that regard. All right, so if we do a calculation here, you can figure out how long this is going to take. So we've got 200 by 75 by 0.1. Yeah, so this is going to take 25 minutes to do. Oh, I didn't set that up well. So I'm supposed to start a new project here with someone in a minute. So we'll see how this works. We're seeing a nice sharp peak here in the cross correlation, so that means it's drift correcting properly. Again, to pull up this information over here, I clicked on Show Hide Collapsible Control Panel. Yeah, so these buttons in TIA, they're kind of a cluster F here. You can also turn on the output window. So this actually goes over the, when it's doing the drift correction here, so you can see for each slice, what it did. And then you can just deselect that if you don't want it there. Yeah, so the interesting part again is the film, okay? Is this silicide, which has a rather unique crystal structure. So as far as our data size, right? So we've got, if we do the calculation here, we've got 200 by 75. That's our total number of patterns, okay? Each pattern is 256 by 256, okay? So if we multiply by 256 by 256, okay? And then we have to account for the byte range, right? So it should be, if I think about this here, so yeah, these data sets are going to be big here, right? So if we, since it's 16 bits, like the Ceta camera is 16-bit, we have to multiply this by 2, I believe, because it's 8 bits to a byte. So we multiply that by 2. And so yes, this data set, when all is said and done, is going to be, let's see here, yes, close to 2 gigabytes, which is not unexpected. Yes, that is right. It is 8 bits in a byte. So, and yes, so the SATA camera is 16-bit dynamic range. All right, so now we're starting to get into that oxide layer. And then we're starting to get now into the interesting part, so, which is the silicide. It's a good idea before you acquire the data to make sure your hard drive has enough space. So if you find your C drive, because that's where it goes to initially, go to properties here and make sure you've got space. Okay, it won't acquire if it doesn't have enough space. Okay, like if you try to do the acquisition and it knows ahead of time it's not going to work, it will bark at you. But that's what you can just check to make sure. So if it's giving you that message, check to make sure that your C drive has enough space. Yeah, so this is looking really neat now. So yeah, there also is, because we're drift correcting, there's also a time penalty for that, right? So each time we have to collect a new drift image, we have to do the correction, that also adds to the total time. But just looking at the image here, I mean, it looks like it is correcting well. If it's not correcting well, usually you'll see like streaking left to right, not so much vertically, right? Because it's it's correcting at the end of every row. So there is a way, once the data is done collecting, we can insert an image position marker into either this orange box or the stem area here, and we can then move the marker around and see the pattern at every pixel, or any given pixel. There isn't a way on this to sum all the patterns, unfortunately, at least not that I know about. Maybe somebody can add that in the comment section, if maybe that does exist. I haven't found a way to do that. I know you can do like a sum spectrum if you're doing EDS, but that doesn't work with the patterns for some reason because it's a CCD, and or not technically. Again, CMOS, but that must be my people saying they're here. I wasn't expecting it to take that long. I really wasn't. Okay, so this is going well here. So I wasn't counting on this taking quite as long, but there was a lot to explain. So I'm going to just let this run here, and I'm going to keep letting it run until I have to. Well, I'll just cut the camera. I'll come on quickly and say I'm just leaving it. I'll let it keep collecting, but I've got my my customers here soon, so or now actually. So I've got to go meet them and pay the bills. So if I don't talk to you again. So hopefully you found this useful, and I may do a follow-up video showing again how to do some basic manipulation with the TIA 4D STEM dataset here. Like I said, how to show where you can just drag around inside of this and see the individual patterns. It's pretty quick, but you know it's still pretty useful. So, all right, so take care, everyone. Hey everyone, I'm still here. Got some stuff to do with my other customers here, so this is still gonna run here. Maybe able to let it go to completion. So we'll see. right, we are almost done here. Looks like we got just a couple more rows to go. The drift correction worked really well. So yeah, we're now down into the substrate, obviously. Good old silicon along the most studied zone axis ever. Yeah, you can kind of see how this is, like you have to rotate it counterclockwise to align with the normal to the substrate there. So, all right, last line. All right, and then I'll be able to show you. Now it should get rid of these reference images and just keep the stem area and the drift corrected image with the boxes as well as the diffraction patterns. Yep, or I could be wrong. All right, so it kept all of these. All right, no worries. All right, so then the last thing I want to show you here is if you grab the image position marker tool, you can click either in this box or in the stem image. Hold down Alt, click, hold, and drag onto the pattern. And now you click and drag and you can see where or what the diffraction pattern is at any pixel inside of the map. Okay, you can do the same thing on the reference image here. Alt, click and drag, and now you have it inside of both of those. Okay, pretty neat. Okay, so that is the tutorial for doing 4D-STEM with TIA. So thank you for bearing with me, and I hope you found that useful.